Hello, can you hear me back? Excellent, excellent. Thank you, Chairman, for the introduction. And thank you, Professor Ali, for the invitation to join today. And not just only present this update on a global alliance we are been working on for the last few months, but also for your hospitality and for your kindness, you and your team. You all been one of the best hosts in these conferences, so thank you very much for your invitation. Today is my talk will be about a new initiative, a global initiative on superconductivity. We've been hearing a lot of activity this morning. We have excellent presentation on some of the applications, some of the challenges, and some of the promise of superconductivity. So today I will try to share with you a vision going forward with superconductivity. Currently, I have over 33 years experience in superconductivity and cryogenics. And 2 years ago, I established my own company, consultancy company, but also I joined Lancaster in part-time as a professor in business development of low-temperature applications, and also a non-executive member, director for IntelliConnect, working on quantum technologies. So I have very diverse expertise, and since I am retired to start this business, I have the freedom to think freely. And today I will share with you what we come out with a lot of colleagues. Some of them are here and some are not here on the Global Alliance. So today I will start with the challenge and then briefly touch on the zero carbon emission targets, very briefly an overview of superconductivity, and then I will present this Global Alliance and the summary. So the challenges are familiar. Climate change is a reality now. No one claims it's a fluke. No one claims it's just accidental. It's happening, and it's happening in extreme conditions. One striking feature is this last year, Pakistan was underwater. 30% of Pakistan was underwater. That's massive. A large country completely underwater. It's not an accident. So the climate change and the environmental changes are real and affecting us in so many ways. United Arab Emirates, if anyone been there, in July they had floodings. Antarctica is melting, and California is having extreme flooding as well as fire. So really the challenges are enormous. And we believe superconductivity will make a difference to address some of these challenges. More importantly, there are 17 strategic development goals by the United Nations. Every single country, I think over 200 countries, signed to these goals, and they budget every 5 years or 10 years to address these targets. So these targets are international, global, and these targets affect all of us. So all the funding, all the budget, all the policies, regulations are driven by these 17 development goals. What I've done, I've taken some of these goals and I've highlighted in green where superconductivity will make a difference. For example, on zero emission, on healthy, resilient, and biodiverse environment, safe, sustainable, and productive water resources. I wouldn't be surprised in 20 years we will start to see wars because of water. In fact, last week I did something. Europe is going to suffer from water shortages. So these are real threats to our societies. And reduce the impact of major bushfires and so on. These are, the green one shows where superconductivity will make a difference. Indirectly in blue, but there's other core technologies which will benefit. And to that effect, we developed 4 smart markets where superconductivity will impact these 17 development goals. The electricity computing market, industry, energy, power and transport markets, the healthcare market, and science markets. Science market is very critical for our future, discovering new materials, understanding their behavior, controlling them, and so on. This is a nice picture Bloomberg has released 2 years ago. These are showing the estimated global generation mix. These up till 2020, these are real figures showing how much money we are spending on coal, gas, oil, nuclear, and hydro. And what it shows that, and this is done in the context of achieving the 1.5 degree target by 2050. What it says that by 2050, we will still be relying on coal and gas, and this 1.5 target is out of the window already. So something fundamental has to be done, something critical has to be done. The other interesting feature here is showing solar and wind will grow very quickly. I don't believe conventional materials will address that increase in supply of solar and wind. The third observation, this here showing almost 30%, 27% of the target for fusion. So fusion is addressing this massive $6.6 trillion investment in generation of electricity. That's why we have almost 35 private companies now working on fusion, 14 of them on superconducting applications. And the winner, and that's why we have so many of them, the winner is not only just because getting a Nobel Prize, the winner will be tapping into large markets. So we have to link superconductivity to the social and economical targets of our future. The solar and wind is an enormous market for superconductivity, almost over 10 trillion by 2050. And really, that's where the opportunity for superconductivity, it will make a difference, and it can. So zero carbon emission, there's an urgent global need to address the climate change, as already been identified, like burning fossil fuels, deforestation, and industrial processes are the cause. And we are seeing the evidence of that climate change, like rising temperature, extreme weather events, and so on. And the scientific message is clear. The scientific message is saying that we have to do something. And to that effect, there's a Paris Agreement. This is all United Nations countries signed to it in 2015, 2016, committing to 1.5 degree increase by 2050. Very ambitious, but they say it's very feasible. And this ambitious and feasible milestone really is dictating some of the funding and the governments. And we are starting to see that happening. For example, Airbus committed to an electric plane by 2035. They said that we are going to electric plane. We start to see, many of you are seeing these effective regulations. To limit global warming to 1.5, we need to be peak by 2025, and they start to decline 43% by 2030. We are not going to reach that. We are already missing that. There are some panic in some of the governments that 2050 really is might be not viable if we continue doing what we are doing. The more important observation is the strategies have to be covered by these Paris Agreement, renewable energy transition, electrification, energy efficiency, sustainable land and use, agriculture, and circular economy. And I highlight in green where superconductivity will make a difference. All these four will be reliant on superconductivity. So quickly, I will show an overview of superconducting application. We all familiar with, many of you are working on it. In life sciences, energy generation, quantum computing, healthcare, so many applications has been enabled by superconductivity. And that's dependent on materials. So there are over 5,000 superconducting materials being discovered so far, but only 6 practical. And majority of them are really, majority of applications rely on neodymium. If you are working up to 10 Tesla, you don't need any of the others. Neodymium allows you to higher field, and some of the fusion program like ITER and high energy physics and high magnetic field. And then we start to see the emergence of high-temperature superconductors, and we start to see the compact devices coming. We are starting to hear about peptides. That's quite promising material, but it will give us a TC of not more than 50, 60 K, so you need to rely on cryogenic below 20 K, I think. We start to hear about room temperature superconductors. Yesterday we heard about the graphite at room temperature. But the message is the continuous research into materials still mean that in the near term we are relying on LTS and HTS up to 20K for high field, probably 50, 70K between 5 and 1 Tesla. And this is diversity of application of superconductivity, but really only MRI made it commercial. The rest are still in the lab, the frontiers end. We are trying to understand how we can take them outside the lab. High energy physics for large-scale application, fusion, light ether, but the rest are still frontiers end. And the promise coming from power and energy applications and also from superconducting quantum computing as an example, but there's a lot of diverse applications here which will make a difference. So the opportunities are large. I'm expecting we'll start to see serious introduction of superconducting application into many of these emerging markets. And this is an example of if superconducting can make it. MRI is a good example where commercial ecosystem is well established. It was over 40 years since the first commercial magnet being developed by Oxford Instruments. And you could see it was at TRL level 6 when it started. And you could see the journey. So I joined Oxford here in 1989 working on these MRI systems. It was technically challenging, production challenging, and we were doing about 100 systems a year. Now it's the global production of superconducting MRI systems about 4,000 every year. It has a full ecosystem, supply chain, regulations, quality control, cost. The price has been dropped significantly when it was a few of them to now. So very easily you can get a 1.5 Tesla now within short notice. The other observation that when this was established, it was penetrating only 5% of the diagnostics market of healthcare. The rest was X-ray and then CT scans. Nowadays, almost 50% of the diagnostics market is MRI systems. And it's growing continuously, and it has made a step change in our healthcare. No one denied that. Healthcare has improved so significantly because of MRI. The second example, this is showing the evolution of MRI systems. Currently, we have 60% of MRIs are 1.5 Tesla, 30% 3 Tesla, and in 10 years' time, it will be the other way around. We'll start to see 60% 3 Tesla and 30% 1.5. And the reason for that, the high field means a high quality image, more precise, more clear picture. It's like a telescope or microscope. It gives you a better image. But also there's a research into going to higher fields. 7 Tesla now is a preclinical stage. Currently hospitals have it, but they are not really clinical devices. They are preclinical, so you have a license to employ it. And literally waiting for the regulations to approve. So it takes between 7 to 10 years to get a license for these machines. And last year, 2021, ScGA has introduced the 11.7 Tesla, which will make a revolution in terms of our healthcare, especially for Parkinson's disease and brain diseases. That will give us really a new opportunity to address some of the challenges like epilepsy and so on. Another promising application for superconductivity is cancer treatment. This is on the increase, almost 19 million new cancer cases in 2020, and by 2040 will be 27, large number. And these are real numbers, and the cases are increasing, and the treatment are very tedious and critical and might be detrimental. And particle therapy, I call it, like carbon, proton, is a promise for these things, but they're expensive. Not many people can afford it, not many countries can afford it. The cost between 50 million to 200 million. And superconductivity will give you the opportunity. That's where the next expansion of healthcare, how we can get cancer treatment with superconducting devices into hospitals, like MRI. So these are examples of some of the LTS devices, some are new in the SGS plan, and the challenge is how to take them smaller in size and smaller in footprint and cost. Fusion, we heard quite a lot about fusion, so they gave a very good overview. And really what I want to say, the future is for compact devices, although it's not going to be in the coming 5 or 10 years, but there's a lot of progress, and that will be enabled by superconducting materials. A lot of promise on power applications. This is showing the TRL level, and currently you can buy a fault current limiter. Not many. Every year they made about 10 to 20, and cables. We start to hear about cables more than 10 kilometers long, like the one in Munich, and they are starting to be happening. These are quite advanced. My expectation in the coming 5 years, start to see more transmission lines, especially with the expansion of wind farms and solar farms. This is an example of the impact of superconducting wind farm. You can see the size, conventional versus superconducting, and literally you can double the performance of these wind farms, retrofitting, not just only new ones, with superconducting components. Storage and transmission lines start to make a difference. And there's almost 70 cable projects now worldwide in Europe, US, and South Korea, and China. And I'm expecting this will be grow much faster in the near future, especially if the initiative goes ahead. Another example is not of industrial machines. This is a real example of a magnetic separation for in a mine in Amazon, a very harsh environment. I mean, it's a harsh environment for human, but without superconducting, this is using helium in a mine in Amazon, and responsible for clay purification. The same technology will be adapted for water purification, if you can make it compact and cost-effective. Transport, that's going to be a big thing. Really now big in Japan and China. Europe and US are still not keen on that, but really will make a big difference and see this investment going into that. Electric planes is happening now and partially driven by the zero carbon emission. The zero carbon emission is forcing airlines to think about reducing their emissions, and Airbus and Boeing are committing to these electric planes. Sorry. Here you will start to see the expansion on electrical transport, electric planes, and it's expected that will be 39 new deliveries by 2030. And currently we start to see electric planes using batteries, but it will be between 2 to 10, maximum 20 passengers, really for a small scale. Hydrogen is being promised as a source of electric planes, but that will give us planes up to 70, 80 passengers. And the challenge is how to get 150 passengers, and you can't do it without superconductivity. You need hydrogen, probably, but you can't do it without superconductivity. Another big impact of superconductivity, Professor Irfan gave yesterday a very good overview on quantum computer. For the last 50 years, we've been relying on coherence and localization of quantum phenomena. This has been driving like X-rays, superconductivity, nuclear power, lasers, semiconductor. And that's what we call quantum 1. Nowadays, we are going to a new revolution of quantum 2, which is driven by superposition entanglement. And it's already enabling a new promise into atomic atomic clocks, sensors, metrology, measurement at quantum scale, imaging, computation, and communication. And this is picking up a lot, big momentum now. In the last 4 years, 10 billion euro has been given by government to accelerate quantum technologies. The promise to have atomic clocks within 5 years and over 10 years quantum computers. So there's a lot of investment into that, and superconducting will be a critical player in this journey. Why superconducting will be critical for digital technology? It will offer almost more 100 times energy efficiency. This fits exactly with the zero carbon emission. It will be smarter, much powerful machines, and will be cheaper. So that will be superconducting will be very critical. Not only quantum computing, but also classical computing. This is an example of some big players like Google and IBM demonstrating their roadmaps to have universal quantum computer by 2030. Already IBM released this year 433 qubit device, Google 72 qubit, and the race is on. And I'm expecting that we will start to see significant results coming out in the coming 5 years from this research. So let's give you an overview on cryogenic, on superconductivity. On cryogenic, I'm just showing here most of the applications of superconductivity work at 4K, sometimes at 2K if you want to go to high field, or like the high energy physics at low temperature. We start to see the emergence of application at 20 Kelvin, hydrogen enabled by hydrogen. And I'm expecting HTS will serve that market between 20K and 70K. For the transmission, you will stick with the 70K. For some of the other applications with high critical density, you might end with 20K or even 40K with single-stage cryocooler, which will make a revolution in terms of applications. The market of helium is growing continuously, but still dominated by MRI use. 32% of MRI of helium is used by MRI, and it's very critical for the future. And HTS will enable us to go to other cryogens and enable more applications, which will expand the use of these technologies. The markets, I just want to share with you where the markets now is still dominated by MRI, followed by science, research, and development, and then you have some NMR and some fusion and electric transport. And by 2030, 40% of the increase will come from emerging markets. So I'm expecting it to be doubling by 2030, and that's without the initiative. If we continue doing what we are doing now, if we introduce fast-track introduction of superconducting application, that very easily becomes even 4 times bigger. This is another nice picture showing the evolution of superconducting technologies, showing here the number of patents every year. This is a global figure, roughly about 1,000 patents every year, 1,500. And it's shown in the last 3 years before COVID, the sudden increase almost doubled in 2019 before COVID. I have only the analysis 2021, I'm working on a new one, but it showed that there's this trend indicates there's a serious interest in introducing a new solution of superconductivity. And that's even nicer picture. It's showing where the patents are concentrated. Still large number on magnetic field, how to develop new applications, different uniformity. Superconducting wire, I showed a very nice picture about the number of suppliers and a lot of patent and IP is developed in that regime. Currently it's reaching out and so many things. So that allow me to come and talk about the Global Alliance we are proposing. How much time I have?
Nearly 30 minutes.
30 minutes. Good. So there will be good time for discussion. So the vision. This is a few of us In the US, in the UK, in Europe, and in Japan, we've been debating that for the last few months, and collectively we came out with a vision. Superconductivity has already enabled, I will read that because that's really what is guiding our activity now, enabling major advances and capabilities such as MRI, NMR, high magnetic field research, and high energy physics, which otherwise would not be possible. We will not have these without superconductivity, and that's a fact now. In the future, superconductivity will provide means towards zero-emission targets, for example, by enabling fusion power, expanding usage of wind power, and facilitating zero-emission transportation, as well as enabling new technologies such as superconducting classical and quantum computing, water purification, new medical diagnosis and therapy tools, and new scientific breakthrough. And to summarize this in just 2 words, we want to take superconductivity from the frontier end, where it is now, about for MRI, into the mainstream technologies, like semiconductor industry. You have the semiconductor industry in your pocket. How much we can use superconductivity to enable that. And that's an opportunity for us. We have gained so much expertise, we have so much evidence that it can make a difference, so can we do that translation? And to do that, we want to use the environmental challenge as a driver for smart industrial power and transport solutions, healthcare challenge, big demand for data. I mean, the increase in data is enormous. We are creating data as we are talking now. And smart science, I think, is critical for all these applications to continue discovery in new materials, in new applications, new techniques in science, so that it allow us to take it into the nanoscale in an engineering way. These markets connected with an initiative on Superconductivity for the Future will allow us to link between the emerging markets, the United Goals, and the grand challenges. So to that effect, we are proposing to have an initiative for Superconductivity for the Future. And to do that, we are proposing partnership between the community, all of us working on superconductivity in industry, in research, and in the national labs, and with the investors. Come closer to the investor, like government funding, private funding, and innovation bodies. And the missing thing from current discussion, the end user. We want to bring the big industrial to that. Because currently, big industries having their own roadmaps, and if it doesn't give return in short term, they would be reluctant to be an active player. They are waiting for the maturity of the technology before they really invest. We think there's an opportunity to work together to develop that partnership. And I don't believe any new initiative will go and a new technology will be delivering without having partnership between the public and the private. So even NASA, 20 years ago, it would be a heresy to see NASA using a public company to launch satellites. Nowadays they are doing that as a routine, even in that level. So going forward, the public will not offer a massive amount of money without involvement with the private sector and the industrials. So where we are in progress, so we are proposing a program to deliver national and international initiatives on superconductivity for the future. The partnership with the decision makers, funders, and big industrials. We need to develop white paper to communicate that message and develop a 10-year roadmap so that people can understand the investment route. We are proposing to have options for national and private funding of the proposed grant challenges by 2024, develop consortium partnership between the various players, stakeholders, and have a global summit. It's like the COP 28 and 29, where decision makers with industrialists and specialists and the funders come together and adopt options for this initiative. And then adopt these options with a target more than 1 billion for 10 years. Depends how much we are ambitious. So, and then we're followed by going to Davos. That's where most of the decisions for the future are taken nowadays. COP29 and Doha Forum. And then for focused market research. In progress, we are working on the final version of the white paper. This is now the first draft for 7 white papers being completed. Now we are finalizing them. And we are developing a high-level document for business leaders. We are developing a reach-out activity and initial plan for delivery. So current status, over 95 senior experts now part of this alliance. We have 7 white papers. We already have 2 special plenary sessions at UCAS and ABD being given. And then we are having plans to have one-day events in Washington, in London, in Brussels, and in Japan and Korea. And there will be a workshop in Oxford to take that stock of that information and plan for the summit. These are the active players, over 30 industrial players, university, 25 research institutions worldwide. And these are, we have an international organizing committee from UK, Europe, Japan, and US. These are the 7 working groups with the conveners from different people, different locations. And we have international editorial board now going through the white papers, which is guiding how we want to take this white paper into a business statement. We have been doing that for the last 15 months. Now we are at the stage we want to finalize it and go to the workshop in Oxford. That's the timeline for our, how you can support and engage. This is an inclusive initiative. If you are interested, you can help. Please contact me or contact any member of the ScGA. Susie is here, you can talk to her as well. And to summarize, superconductivity is entering an exciting phase of development and exploitation from the frontier end to the mainstream applications. Superconductivity will impact our future in so many ways and has the potential to lead to a new industrial revolution. And I will finalize by thanking some of the people who've been actively been sponsored by Oxford University, by IEEE, by ESA's IOB, and British Cardiac Council. And thank you.
Thank you. We are open for questions.
Thank you so much for this beautiful talk. My question is, you mentioned, we heard yesterday, room temperature superconductivity in graphite. In which applications of the ones you mentioned would you see the most immediate applications of such a technology?
For room temperature application, it's like anything you can do with copper.
No, I mean with graphite particularly.
Graphite.
It's not a simple material.
Yeah, I do think what we have heard yesterday is ready to be a practical application. So let me take you to that slide. Can you take me? Sorry, can you take me to the... So that's a good question. And there are almost 5,000 superconducting materials being discovered so far. Only 6 are practical. When we say practical, they can use it as an engineering tool. So the ultimate aim is to use these materials like either like wires or tapes or even plates or bulk. These are the configuration you can use them. I don't think graphite at that stage we can put it into any of these. What I heard yesterday, I don't know what format it will be and where it will be used. That's one thing. The second thing is I want to go to the materials table. And from engineering point of view, you have to think about system integration. That's the other challenge. So to understand this, to allow you to exploit these materials in an effective way, you have to make sure that the environment, the system integration, determination are fully understood. And it took many years to understand how to make these devices, use them for granted. Yeah, so if I take this example, these are already in our paper. There were 2 years ago another paper about room temperature under high pressure. So all these activities you see here, or you see here, like neckties, you can make more than 50 meters in neckties now. These are still a lab material, and we need that work on lab environment. But to take this technology to a practical application takes time. So for example, it took almost 50 years from the discovery of superconductivity to make malleable titanium, almost 50 years. And it took us from 86, the high temperature superconducting was not discovered. We are just start to see some of the, what I would call large scale application, like honorable fusion and power transmission. It took almost over 30 years. So it takes time. So a graphite still has to demonstrate what form it will be, I don't know. What I've heard yesterday, I don't know what form. And that will decide the scale and the application you can use. If it's going to be bulk material, it will be limited because you can make large bulk devices. If it's wire, it will be extremely very attractive because round wires are still the most preferred one to make many of these devices. If it's tape, we have to come with configuration like what they are doing now with these cables. For example, like fusion, they are doing these sophisticated conduit cables to allow integration. So it depends really in what format it will come.
Thank you. Any other questions?
Yeah.
Knowing the fact that you're coming from MRI business when everything is titanium, very rarely is titanium, how do you see the percolation of the, also penetration of this market by ITC tapes, which are maturing now?
It's a very good question. Very good question. At the moment, MRI are very stable. It's a product. It's a full ecosystem. So for any other technology, you need to provide that. What's the advantage? So, like HTS, it has to be cheaper, and it has to higher temperature will be attractive because it will reduce the size of these MRIs because you have the vessels and so on. So that's if the price goes down to enough to make it competing with niobium, people will accept it. The other attraction for HTS is making portable MRIs. That will be a big market. At the moment, you have to travel 70 miles to have an MRI. You have to live within a hospital within 70 miles. If you are over that, you have to come overnight. That's globally, probably more for some people. So the big expansion for MRI is compact systems where you can have them in even surgeries and not hospitals. So that's where I think the opportunity. The opportunity is we can have compact systems delivered to rural areas. It's not only just Europe and the US, we want to reach to Africa and Asia and other regions. So how we can get the health care to the global population. So that's the opportunity.
So there will be some.
There's a big room. It's how to engineer it.
Okay, thank you very much. So this is the end of this session. Thank you, speaker. Thank you for joining us.
Thank you.